Yeah.
I was just wondering, does it have to be graphene or
No, no.
like so?
Gallium arsenal, apparently some people see similar thing. Some boron nucleic, they make double layers. There are a set of measurements with double layers too. There is much more here, and there are a lot of things going on now, which are probably in different states. But understanding is that graphene is not unique in this respect. A lot of high mobility materials look like this. Yes.
Coming back to my previous question, so in a sense you are cheating, because if I look on in the ballistic regime, the conductivity that you're describing is what we call two-terminal conductivity. Namely, you apply a certain voltage away where you have dissipation, and you measure the current. But if you were measuring the difference in chemical potential across your constriction, you would find, in fact, infinite conductivity.
Right, but then again...
No, just a second. Yeah. So now it's a question, how do you measure the difference in chemical potentials?
I'm cheating microscopically, but macroscopically experimentalists do not cheat, and I am a processor, so I am
no,
what I define conductivity the same way in both cases. Namely, I define conductivity as a potential applied at the far ends of my okay, that's my potential, and I have a current. It's a totally macroscopic measurement.
But it's not a property, but then the dissipation takes place at your contacts. That's where the resistance comes from.
If I'll be interested in dissipation, then I would really need to resolve this. But come to think of it, I'm a simple electric engineer. I take a piece and I have a small opening over there, and I apply potential and I measure current. Then I make this opening a little bit larger, then I make this opening a little bit larger. Then I ask what happens. And then in some regime it just linearly changes with it. And then it changes into quadratic. It went linear, then it went quadratic. Then if I do conductivity or resistivity, then I see that it would be other way around, right? So it would be, and that's it. It's a macroscopic measurement where potential defined far away and current defined also far away. But you realize that there is a lot of sub-ballistic. It will be interesting what actually happens inside. I would recognize that ballistic flow dissipates at the edges, and viscous flow dissipates at every point. Viscous flow dissipates at every point of the flow.
Yes. And if you were comparing, if you were really defining the four terminal, if you were doing your electrical measurement properly, namely apply current externally, but measure the difference in electrochemical potential locally across the constriction, which is really the conductance of the constriction, you'll find that the ballistic conductance is infinite, is not finite.
Absolutely.
And then this surprise disappears because your conductivity will still be finite.
Yeah,
this conductivity is going to be infinite.
No, I'm not saying that there is a surprise. Frankly, for me, as a Gaussian Poisson transition is something which I learned, as an undergrad. That if you increase interactions between particles, they avoid obstacles. That's it. That's what is for me, right? That's it. I also find it non-trivial. Right? And you're right that the moment I start to look at it from a quantum perspective, honestly, there is also natural. There is no big surprise. And still, you enjoy it, right?
We simply don't take yes for it.
But I mean, I'm a physicist, I'm supposed to cheat something, right?
What corresponds to negative resistivity in viscosity?
Well, viscosity makes negative resistivity possible because it's something which lets you to drive current non-locally. You can drive current here by electrons moving here, and then you can drive current here against electric fields. That's what viscosity does. It's a non-local driving. It's kind of, that's why it lets you have negative.
So can you speak about negative viscosity?
No. It's it's a parameter, and it's very tempting to do analytic continuation, consider new complex, and then going into the tricks that we do, for example, in critical phenomena. I never was able to get anything meaningful. It's very tempting, and I don't know, of course, materials don't exist. Now, in a medium out of equilibrium, we don't have negative. You have negative viscosity because in two-dimensional flows, your energy goes from small scales to large scale. But it's not really, people like to talk about negative viscosity in the sense that, for example, two-dimensional turbulence produces big vortices, right? So you can say, okay, this big vortex actually has negative viscosity, that instead of dissipating energy, it gets energy. But it's not this, and it's not the viscosity, it's different. I'm probably very critical.
Okay, let's thank Richard again.